This is going to be a quick tutorial of how to use Xilinx ISE to perform simulation of a Verilog design. In our case, we're using Xilinx ISE version 14.7, but this equally applies to any of the recent versions of ISE. We've already created the Verilog describing a 32-bit adder and a test bench for that adder, so we're going to walk through the main process of how to use the ISE tool itself. So we're going to create a new project. For our project, we have a specified location here. We're just going to use an example of an adder simulation tutorial. And we need to make sure we select HDL as being our top level source type since we're doing a Verilog example. On the next page, they want you to select some project settings specifying what type of board you're using or FPGA. So these aren't all that important for us if we're just doing simulation, but we're going to choose our target device anyway. In our case, our target device will be a Vertex 7. It's the XC7VX330T with a package FFG 1157 and a speed-3. So once we have all of these settings made, we can then go next. We'll get a summary of this and we can click Finish. We now have an empty project here and we need to add our source file. So there's a couple ways you can add the source file. There's some icons over here you can use to create new source file or add existing ones. You can go to Project and create new source files or add existing ones. Or you can go to the device itself here, right click on that and say Add Source. So we're just going to navigate now to our source. We have both our 32-bit adder description and our 32-bit adder test bench. And we're going to open both of those up for our project. So in this case now we have this component. If you see under the association you have a couple options. Either it's for implementation, that's if you actually want to synthesize this and put it onto an FPGA board, or you can just do simulation, or in some cases you want both. So for our adder itself we want to choose this for both, but a test bench is only meant for simulation, so we're going to mark that as simulation. Once we've done that, we can see over here that they've added the components for us, but we're only seeing the adder 32 right now. And that's because our default view in Xilinx is the implementation view. So if we switch this over to simulation view, since that's our goal, we'll now see our top level component is our adder test bench. And if I expand that, I can see under this we have our 32-bit adder itself. So if I double click one of these to open it up, we can take a brief look at our test bench here. The couple important things are I have my component instantiation here, so I have an adder32 component with an instance name of adder32_0, and I've mapped the inputs and outputs to the internal registers and wires that we've declared up here. In this case, I've used an _T for each of these names, so if I'm looking at the simulation waveform, I know that these are the signals inside the test bench and not the names of the signals inside the adder itself. This uses an initial procedure to do a set of test vectors. We only really have 4 test vectors here. A good test bench would have a lot more. In each case we have a setting set for A and B, and then we have a small delay. In our case this is a 1 time unit delay, where that time unit is specified up here as our time scale, so essentially we have a 1 nanosecond delay in between each of these. If we take a brief look at our adder, we have a 32-bit adder. We have 2 inputs A and B and a single output S for our sum. We're not dealing with a carryout in this design, and our implementation is simply a behavioral implementation where we're simply assigning A plus B to our output S. So to simulate this, what you need to do over here in your hierarchy is choose the top level component you want to simulate. In our case that's going to be the test bench. Once I click the test bench, down here in the bottom where I have my processes, we can see that we have the simulator. So I'm going to expand that and we'll get 2 options. One is a syntax check, so it's always a good idea to do a syntax check ahead of time. In this case we passed successfully. And then I can do a simulate behavioral model. This will actually do some processing of the files and open up the simulator in a separate window. And so now what's happened is we have our new simulator here. It's called ISE in a separate window. It's already started up, and the default setting right now just simply simulates, adds any signals from the top level component, and it simulates it from a predefined period of time. That's sort of just the default behavior that ends up happening. So for us, we're going to go up here, and our first thing is we're just going to reset this simulation here. So I can restart my simulation. I have a blank simulation now. If I saw these values, these are printing the values out in binary. It's not so useful for reading the values in this case. So I can select all three of those, right-click on this and change my radix to an unsigned decimal. And now when these are displayed, I'll actually see decimal values instead of binary. These are the only three signals we want to trace right now, but we don't need to run this for 1 microsecond. Instead, we only had 4 test cases. They were each 1 nanosecond, so I can add 1 more nanosecond at the end there, and we'll just simulate this for 5 nanoseconds. So if I click this button, it'll only simulate for the specified length of time. If we simply click the simulate button, it'll keep simulating until we tell it to stop. So for our case, we want to simulate for a specific length of time. So we can do that, and now we can see our waveform now is generated here. The waveform is fairly zoomed out, which doesn't allow us to see it very well. So I have a couple options. I can manually zoom out, clicking this button several times. Or the next button here allows us to basically zoom out to show the entire full view of our simulation. Our simulation was short enough it's pretty easy to see. So here we have our test bench where we're adding 5 and 10, 50 and 7, 1,000,000 and 34,991. And so this works out well. We can see the waveform. We can click on these individual signals. You have a lot of options for measuring time between signals that allows you to sort of examine the exact behavior of your design. And that's about it for setting up a basic simulation.